welcome to the third of our July lectures for 2011, celebrating the unexpected discovery of superconductivity 100 years ago. My name is Professor David Jamieson. I'm the head of the School of Physics and the organiser of the July lecture program. It's my enormous pleasure tonight to introduce my colleague, Professor Ray Volkas, to give tonight's lecture. In the previous two lectures in the program, we've looked at the history and the physics of superconductivity. We've looked at the remarkable applications of superconductivity to technology pioneered by the CSIRO. But tonight we are turning to much deeper and broader and more profound consequences of superconductivity. Tonight's speaker is one of the world's leading experts in some of the most profound questions of our time. Ray works on deep problems involving the standard model for particle physics, the consequences of higher dimensions, the phenomena that occurred way back at the beginning of the universe and how those phenomena have guided the evolution and the ultimate fate of the universe thereafter. Ray has a distinguished career in research that's been well recognised, including the Pawsey Medal in 1999, and last year he received one of the highest accolades it's possible to receive as a scientist in Australia when he was elected to be a Fellow of the Australian Academy of Science, a distinction awarded to very few people. This year he became the director of the Melbourne node of the Australian Research Council Centre of Excellence for Physics at the Terascale. This consortium involving collaborators across Australia and overseas will be working with the machinery at CERN, where they are seeking to recreate conditions here on Earth that haven't existed since the time of the Big Bang and answer some very fundamental questions about the origin of mass. But in addition to being a distinguished researcher, Ray also has a distinguished track record as a lecturer in physics. He is renowned amongst his students for the excellence and clarity and depth of his lectures. As well, the students appreciate his dry humour. So, Ray, I would like to invite you to the stage to take us.
Well, thank you, David. After that introduction, I feel that the rest of the evening can only be a disappointment. But I'll try to prevent that outcome from occurring. So today I'm going to tell you about the superconducting universe and as a subtitle, breaking symmetry. I'll only have one slide on breaking symmetry because that's actually very hard to talk about. So I'll only give you an impression of what that's all about. But I'll talk fairly thoroughly about the possible relationship between superconductivity as discovered in ordinary materials, ordinary metals, and the possibility that the entire universe is in a different sense a superconductor. And this is a great story, and this is what the Large Hadron Collider at CERN is all about, and I'm sure most of you have heard about this fantastic new machine that is now operating very, very well. Okay, so the Large Hadron Collider is a particle accelerator. It's extremely large. It's 27 kilometers in circumference. It's located on the border between Switzerland and France, near Geneva. Here is an actual photo inside the tunnel. These things that you see here are magnets. And those magnets, well, I'll tell you about those magnets in a second because they also have something to do with superconductivity. And right inside this big tube is a smaller tube. Actually two smaller tubes, and those tubes carry beams of protons, these beams of protons are very, very energetic. They're accelerated to very high energies, and they are made to collide at certain points around this ring. And at those points, protons collide with each other, and all sorts of different elementary particles are produced, and we hope to unravel certain deep mysteries of the fundamental structure of matter through this experiment. Okay, so in here somewhere are protons. being accelerated and forced to collide. So that's the LHC, or Large Hadron Collider. It is located, it is run by a laboratory called CERN, which is the European Centre for Nuclear Research, but it's actually particle physics research. The nuclear bit is a historical relic. This is actually Geneva Airport, and this is the LHC ring. This is a smaller ring that was doing cutting-edge physics, about 30 years ago, but is now just a booster for the Large Hadron Collider, which, as I said, is 27 kilometers in circumference. You can see that it cuts through apparently areas where there's housing and people living and so on. I have to tell you that the ring is actually about 100 meters below the ground. So it's a major civil engineering feat just to excavate this ring and to make it a tunnel, and then it has to be instrumented with all the magnets and so on that constitute the Large Hadron Collider. And we hope it will do some really amazing physics. Okay, so this is I think it's fair to say that this is the most complicated instrument that humanity has ever built. Okay, I think that's a fair statement. And it was a monumental task to do this. Okay, so in order to bend charged particles like protons in a ring, you need to use magnetic fields. And you need to do this very efficiently. And so one of the technologies that is absolutely crucial to something like the LHC even existing is superconducting magnets. So if you've been to the first two of these July lectures, you will have learned, and I'll go through this again, that superconductivity is the flow of an electrical current without any resistance at all. So the current can flow in a conductor and not lose energy by bumping into atoms in the conductor and turning it into heat and light and stuff like that. I'll talk more about that later. But the importance of this technologically, and for the LHC in particular, is that once you set up a current in a superconductor, it is there for a long, 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 long time. I mean, unless something fateful intervenes, it is kind of there forever. And in order to create a magnetic field, you need electric currents. And so in a superconductor, once you feed the energy in and you create electric currents, they go around for a long, long time, and therefore you have a magnetic field for a long, long time. And because of the nature of the economics of this particular apparatus, the number of magnets that were needed, the strengths of the magnetic fields that were needed, it was crucial to use superconducting currents as the generators of the magnetic field. So it's kind of interesting that superconductor technology is going to be used to discover probably the fact that the universe is a gigantic superconductor, but in a different sense from the way that the metal in these magnets is a superconductor. So I think that's a very interesting connection between the world of ordinary materials, although superconductivity is not that ordinary, and also the universe at large. Okay, so we think, that within a short amount of time, this apparatus is going to discover something that, for the purposes of this talk, will be called the superconducting universe. And this is actually true. It's not usually called that, but it in fact is true. And it is illustrated by this cartoon. You may notice a caricature here of a famous scientist, Albert Einstein. I'll come back to what this possibly has to do with the discovery of the superconducting universe later. My actual task in this talk is to try to explain the meaning of this cartoon. Here is a very, very famous photograph. So around this 27-kilometer ring, there are certain points, there are 4 points, where the two counter-rotating proton beams are made to collide. And when they collide, this is when the new physics, the new particles, the new forces will be created. And around those collision points, you need to produce a big apparatus, you need to put in place a big apparatus in order to detect the debris of the collision. These are called detectors. And this is one of them. There are 4 of these detectors. There are 2 that are of particular relevance to discovering the superconducting universe. And this is one of them. It's called the Atlas detector. and actually the University of Melbourne and other institutions around Australia and the ARC Centre of Excellence, which David mentioned, is a collaborator on this ATLAS experiment. So this is a famous shot. Here is a human. So this is truly an enormous object. These again are magnets. They're also superconducting, and this photo was taken before the interior of this particle detector was filled with instrumentation in order to track elementary particles. So the point of this gizmo is to track elementary particles. The two proton beams come into the detector along an axis, as you can imagine, which is at this axial point here in this detector. And when they collide, there's a spray of particles. These particles go out and they interact with all of this other apparatus. And through those interactions, we can see the particles and we can tell what particles they are. Are they electrons? Are they protons? Are they some other particle? So a lot of the story is about this ATLAS detector and its cousin or competitor, which is called the CMS detector, which is doing very, very similar physics. Okay, I will come back to this exciting physics of the LHC and the Higgs boson, the Higgs particle, this new piece of physics that this apparatus is designed to discover. And I'll explain to you impressionistically why the discovery of this Higgs boson will tell us what is actually the origin of mass, why electrons have mass, why quarks have mass, why all of the elementary particles have mass. This is one of the most fundamental questions that we can ask in nature. Why does anything have mass? And a big part of the answer is going to be provided by the Large Hadron Collider. Before I get to these very foundational and very profound and very deep question, I need to go back and review exactly what superconductivity is. Now, I know that if you've been to the last couple of July lectures, you will already have heard about all of this, but I can't assume that you have, and maybe it helps to hear it, for a third time. So I'll go through the basic idea of superconductivity again, and then I'll try to give you an impression of how that relates to the universe as a whole. So it's the centenary of the discovery of superconductivity, so we have to go back to 1911, and this guy Kamerlingh Onnes, who discovered it experimentally. And superconductivity is precisely the flow of an electric current through a material, typically a metal, with absolutely zero resistance. So it's a really interesting phenomenon and very, very surprising. And it took a long time to understand how this was possible. It was discovered in 1911, and the first detailed theory of how superconductivity works was not developed until the late 1950s, and it was worth a Nobel Prize. So it took a long time to figure out how this phenomenon could actually be understood. But it was known about, it's been known about now for 100 years. So superconducting material has to be contrasted with ordinary material. So if you have an electric current in an ordinary piece of metal, a typical thing is the filament of these things, which are now illegal, all right? You can't buy these things in a supermarket anymore, but a couple of years ago you could. These are incandescent light bulbs, and what you have here is simply a bit of metal which has a current going through it. And of course the purpose of this thing is to turn the energy carried by the electric current into light. It also turns it into a lot of heat. You'll remember if you touch the light bulb after you just turned off the light, you typically burn your hand. So the energy was converted also into heat, but light was the important thing for this particular application. So the electric current, the flow of electrons in the metal, that is the electric current, is the energy carried by that current is being dissipated in the production of heat and light. And this is because the electrons in the current are colliding with the atoms in the metal and giving off some of the energy. So the energy is being transformed from that carried by an electric current into heat and light. And this is precisely what doesn't happen in a superconductor. In a superconductor, there's no dissipation of the energy carried by the current. When you set up the current, it flows forever, unless circumstances change. I should mention that superconductivity is a phenomenon that occurs at low temperatures. So this was not known about for a long time until 1911, because one thing you have to do is cool metals down to very, very low temperatures. In fact, for typical superconductors, very close to absolute zero before you actually observe this phenomenon. So it's not a commonplace thing. And those superconductors that are bending the protons around in the LHC ring have to be cooled with liquid helium, which is something that is a liquid only at temperatures very close to absolute zero. So it's quite a technological feat and an engineering feat to actually construct all of the cryogenics to make these magnets work. So why are superconductors so different from electric light bulbs? And the answer, because of quantum mechanical effects. Okay. So, the actual physics of superconductors, as I said, took about 50 years to uncover, a little bit less than 50 years to uncover, and it's not obvious. People like Feynman were very puzzled by superconductivity. So it requires a lot of technical knowledge to understand properly, so I'm only going to give you an impression of how superconductivity can happen here. Now, one of the important aspects of quantum physics, so quantum mechanics or quantum physics, is the way that elementary particles and small pieces of matter behave. Quantum mechanics is the physics you need to use to understand atoms and molecules and nuclei, and indeed elementary particles, as I'm mainly talking about here. One of the features of quantum mechanics is something called the Pauli exclusion principle. If you've ever done high school chemistry or something like that, you've heard of the exclusion principle. You remember that when you're thinking about an atom, you have shells, you have orbitals, and you have to fill those shells or orbitals with electrons. And you can have a filled orbital, and then you're not allowed to put any more electrons in. And this is one of the things that causes ordinary matter to be stable. The fact that you can't arbitrarily pack huge numbers of electrons into the lowest energy state of an atom, for example. This is called the Pauli exclusion principle. It says that at the quantum mechanical level, no two electrons can behave in exactly the same way. So what we have here is a depiction of energy levels. Another feature of quantum mechanics is that there are discrete energy levels, and the energies in between those allowed energies are not allowed. Okay? So what we have here is a bunch of energy levels, and electrons are examples of elementary particles called fermions. This is named after an Italian physicist, Enrico Fermi. And fermions have the characteristic that you can't put two of them in exactly the same state. So what this is illustrating is that if you have an electron or another fermion occupying this energy level, you can't put another one in there. The next one has to go in the next highest energy level, and so on. So this is the Pauli exclusion principle, and it's absolutely fundamental to understanding atoms and ordinary materials. However, there are other kinds of, and this is, well, so the other thing about quantum mechanics is you have to love cats. Many of you have heard of Schrödinger's cat, which has another problem, but these two cats are obviously very affectionate, and they're trying to violate Pauli's exclusion principle, but violate it. Okay, there's a different kind of particle, a class of particles called bosons, and they're the exact opposite of fermions, and bosons are allowed to be in the same energy state, the same state. In fact, they like to be in the same state. So this is a big part of the story of how superconductivity works. It is a transformation of a situation where you expect fermionic behavior, where electrons are in different energy levels, into bosonic behavior, where suddenly they all want to be in the same state and doing exactly the same thing. And the exactly same thing that they're doing here is conducting an electric current. Okay, so in an ordinary metallic situation, if the metal is an ordinary conductor and not a superconductor, what's happening is this. So here we have a slab of metal, and we put a battery, attach a battery to this slab of metal, and this causes a current to flow. The current is carried by electrons, which have been released from being bound onto atoms, and they're free to move in a metal. That's the definition of a metal. It's something, a conductor, that's something that allows electrons to move. So when you put a battery, attach a battery to a metal, it causes an electric field to exist in the metal, and this causes the electrons to move. But when the electrons move, of course, there are atoms there in the metal. There are the nuclei and the rest of the electrons that are sitting there just in a kind of lattice. And the electrons are able to bump into those atoms. And so the electrons that are carrying electric current are not just, going through the metal unimpeded. They're actually bumping into these things all over the place. They're going backwards and forwards and jiggling about. But overall, there's a sense in which they are moving in a particular direction under the action of the electric field caused by the battery. And whenever these collisions happen with the atoms in the metal, energy is lost. And in order to maintain the current, you need a battery. You need to keep supplying energy into the system in order to maintain the current. Because if you take the battery off, as you know, pretty soon the current is gone. Because all the energy carried by the current is lost into heat and light from the fact that the electrons bump into all of the atoms. Okay, so this is a normal conductor where the current is carried by individual electrons. In a superconductor, the situation is subtly different, but importantly different. In a superconductor, the current is not carried by individual electrons, but it's carried by pairs of electrons that are bound together. Okay? And the important thing is that when you take two fermions and bind them together, they become a boson. So whereas electrons must occupy different states in any physical system, pairs of electrons are allowed to condense. That's the terminology that's used. They're all allowed to exist in exactly the same state. They're all allowed to do exactly the same thing, provided they pair up into these bound states, which in superconductors are called Cooper pairs, named after one of the guys who got the Nobel Prize for explaining all of this in the late 50s. So, most of the time, the current carriers in a metal obey the Pauli exclusion principle, but under certain circumstances, for some metals, when they're cooled below a critical temperature, this is no longer the case, and electrons conspire together into these Cooper pairs, which do not obey the Pauli exclusion principle. And the reason this can happen is because the electrons are embedded in this lattice of atoms, of positively charged atoms. And so this is complicated to explain, but here's a picture of what's going on. So these red things are electrons, and these, what color is this? This sort of greeny yellow color. These are the ions that are there in the lattice of the metal. And these are positively charged. And of course, electrons are repelling each other because they're both negatively charged, but they're being attracted to the positive ions in the lattice of the metal. And when you look at this in detail, and at very low temperatures, what you find is that the repulsion between the electrons can be overcome by the attractive force that is induced by the electrons, a pair of electrons both being attracted to the ions, to the positively charged ions. And because of that, effectively, these two electrons are attracted to each other, but through the medium of these positively charged ions there in the metal. So it's not magic, it's actually physics, but it's very subtle physics. Okay, so this is the general story. So most of the time, this can't happen because when a metal is very hot, these atoms are jiggling all over the place, and this kind of behavior is not possible. But when you cool the lattice down, and these things stop jiggling, for some metals, this is what happens. The ions mediate an effective interaction between two electrons that binds them together, and it turns two fermions into a boson. It turns two things that don't want to behave the same way into an object that wants to behave the same way as a similar object. Okay, so in a normal metal, the electrons behave like fermions, and they line up like this in all of the different energy levels and all of the different states in the metal. But in superconductors, the electrons are Cooper pairs, and they do something extremely different. At low temperatures, these pairs of electrons all go into the lowest possible energy state that they can have. This is what is called technically condensation, as I mentioned before. Now, it's important that the Cooper pairs that are all in a single state of motion. What that means precisely is that they're all doing the same thing. And the same thing that all of these guys are doing is conducting an electric current. So you've got zillions of these Cooper pairs, all conducting an electric current. So they behave collectively. You know, in a normal metal, all of the electrons are like individual particles, and they're bumping into atoms, and one electron is doing something that's independent of another electron. They're just independently bumping into things, and they're giving off energy quite independently. But through the magic of quantum mechanics, which I can't properly explain here, I can only give you an impression. When these Cooper pairs are all together in this thing called a condensate, they all behave in exactly the same way. So they become a collective. They're no longer a bunch of individual electrons in terms of their physics. They behave as one entity. And this one entity is coursing through the metal, and it is conducting an electric current. So now, when you have this Cooper pairs all in this condensed state and all coursing through the metal, it could be that some of them are bumping into atoms and are being excited into higher energy states. But the rest of the condensate of Cooper pairs doesn't care. It still keeps going. And so because of this phenomenon, these local disturbances from collisions don't actually disturb the overall flow of the electric current. It's only when you completely disrupt this phenomenon of all of these pairs of electrons all behaving the same way that you destroy the superconductivity. And that happens when you heat the metal, typically. Okay, so basically, so an analogy here, which I've got from an article by a particle theorist called Lance Dixon, and if you're interested in the subject, I think this is a very nice article. It's written at kind of slightly above Scientific American level. I really like this article. I'll give you the citation to it later. The analogy here is a sheet of ice. Okay, so imagine a sheet of ice on the surface of water somewhere, a lake or something like that. So the sheet of ice moves as a coherent entity, and maybe bits of it break off and melt and so on. But it doesn't prevent the rest of the sheet of ice continuing to move. And so this condensate of Cooper pairs in a superconductor is like this sheet of ice. Local disturbances, local breakings off of bits of the ice don't bother it because the bulk of it keeps moving. Okay, so this is my impression of how a superconductor works. And you get absolutely no resistance. Because of this, superconductors display a remarkable phenomenon, which is illustrated here. So here we have a bit of superconducting metal, which is apparently defying the laws of gravity, and it's actually levitating. Okay, but the thing is that this object here in dark colours, beneath it is actually a magnet, and here is an illustration of it. So what's happening is that if this thing were a normal conductor, what would happen is that the magnetic field lines would go into the metal. But when it becomes a superconductor, what happens is that the electric currents, which experience no resistance, so you can set up any electric currents that you require in a superconductor, what happens is that because of the fundamental laws of electromagnetism, these electric currents that are set up in the superconductor do so in such a way as to cancel off all of the magnetic field that is trying to get into the superconductor. So this is what's depicted here. Below the critical temperature, where this particular metal has become superconducting, the magnetic field lines no longer penetrate into the metal, but they skirt around it. This is something called the Meissner effect. And because of this expulsion of the magnetic field lines, there's a kind of buoyancy force, which counteracts the gravity that is trying to make this lump of metal descend. So again, this is not violating the laws of physics. It's just an interesting new example of a physical phenomenon. Now, the existence of magnetic field lines that can stretch for very, very long distances is precisely what you mean by a long-range force. Okay? Like the force of gravity between planets. It's a long-range force. It can go over long distances. What you need is electric field lines that can propagate for long distances in order to have a long-range force. The fact that magnetic field lines can't exist inside a superconductor because there are currents that are created automatically to cancel them off. What this says is that inside a superconductor, electromagnetism is a short-range force. Outside a superconductor, electromagnetism is actually long-range. Usually you don't notice that. And the reason you don't notice it is because there are positive and negative charges around and they cancel each other out. So an atom is electrically neutral because there's a positively charged nucleus, but it's exactly cancelled by a negatively charged electron cloud. So an ordinary atom is actually electrically neutral. But if you separate electric charges, then the force between them is in fact stronger than gravity. And the only reason electromagnetism isn't as obvious as gravity is because, unlike gravity, there are positive and negative charges which cancel each other out. But otherwise, electromagnetism is a pretty strong force and it's long range. But inside a superconductor, suddenly this changes. Inside a superconductor, magnetic field lines are not allowed to exist for long distances. And so electromagnetism becomes a short-ranged force. And this is a long development, but this is absolutely crucial to the concept of the entire universe being a superconductor, because that idea is all about making certain forces have an extremely short range, to be operative only over a very short distance. Okay, so in quantum mechanics, the way that charged particles interact electromagnetically is by exchanging a particle of light. You know that in quantum mechanics, everything exhibits wave-particle duality. Everything is in some sense a wave and in another sense a particle. So you're probably used to thinking of electromagnetic waves, radio waves, light. All these things are electromagnetic waves. But when you apply quantum mechanics to this, you actually find that these waves are composed of particles in a certain sense. And when two charged particles, here I've got two electrons, interact with each other, when they repel each other because of electrical repulsion, what they're actually doing is exchanging photons between each other, exchanging particles of light. And these are honest-to-goodness particles, and they have mass, just like every other kind of particle. And a fundamental thing in physics is that when the particle that you exchange to induce a force has zero mass, then that is precisely when the force is long-ranged. So the photons are massless, and that means they're long-ranged. It is thought that the gravitational field, when you quantize it, when you look at it quantum mechanically, is composed of particles called gravitons. We've never seen these things, and maybe we never will, but if they exist, they must be massless because the force of gravity is long-ranged. So ordinarily, photons have zero mass and the force is long-ranged. If they were to pick up a mass, this involves a cost of energy. Remember Einstein's relation that mass and energy are equivalent, E equals mc squared. So in order to pick up a mass, this implies a certain cost. And one of the manifestations of this is that if photons were to have a mass, then electromagnetism would suddenly become a very short-ranged force. This is precisely what happens in a superconductor. The photons, which are massless in ordinary space, in this room, they're massless, but inside a superconductor, conditions are different and photons pick up a mass. The force that is mediated by photons, the electromagnetic interaction, is screened by all of these currents that are flowing in the superconductor due to the lack of resistance. And this is equivalent to the photons picking up mass. And so this is what one has to remember, that there's a relationship between particles picking up mass and the forces they induce becoming short-ranged. And this is absolutely critical to understanding the application of these ideas to elementary particle physics, not to the electromagnetic interaction, but to another fundamental interaction in nature. Okay, so after that sort of lengthy review of superconductivity, let me come to the main point. So this is the grand idea that the Large Hadron Collider is designed to test, and it goes by the name of the Higgs mechanism, typically. So the idea is that the entire universe is like the inside of a superconductor. The entire universe is a superconductor. But the superconductivity is not with respect to the electromagnetic interaction. It's not all about electric currents and electrically charged particles creating currents. It's about a different force of nature entirely. It's about something called the weak interaction. So the weak interaction is another force of nature, different but related to electromagnetism, that induces certain kinds of radioactivity. So here is a typical thing that the weak interaction does. I've mentioned that the electromagnetic interaction does things like cause two electrons to repel from each other. The weak interaction does something similar but a little bit different. So here's a typical process. This is a neutron and this is a proton. Neutrons are unstable particles. They live for 10 or 15 minutes. Okay? And when they break up, when they decay, they turn into protons and electrons and another kind of particle called a neutrino. And the way this happens is that the neutron turns into a proton and emits a kind of photon-like object. But this is the particle not associated with an electromagnetic field, but with a different kind of force field called a weak field. And this sort of particle is called a W particle. And this W particle subsequently turns into an electron and a neutrino. These things are called Feynman graphs, by the way, after Richard Feynman. They're kind of little pictures that nicely illustrate what is happening at the fundamental physics level. They actually illustrate how forces work. They work by exchanging these particles, like photons and W particles. So this is very similar to that picture with some differences. And the most important difference for the purposes of our story today is that weak interactions are extremely short-ranged. We are not aware of them, except indirectly, by discovering certain kinds of radioactivity. But ordinarily, we don't worry about the weak interaction, and that's because it's only operative over nuclear distance scales. Even at the level of atoms, it's not very important. Okay, whereas electromagnetism is very long-range. And so from what I've told you, one possible way that you can imagine that could be understood is that these particles, which are otherwise very similar to photons, are different from photons because they have mass. Okay? And therefore the force becomes short-range. So this is the idea that the universe is a superconductor, and the field lines that would be driven by the weak interaction actually cannot exist, because the entire universe is a superconductor, but not of electromagnetism, but of the weak interaction. And this grand Meissner effect that is operative throughout the whole universe is hiding. It is making it very difficult for us to see that there are certain forces of nature out there, in particular the weak interaction. So we know it's there because we've done very careful experiments, but otherwise you're not aware of it. And you're not aware of it because nature is hiding its presence from you. It's hiding its presence from you because a force that wants to be long-range, just like electromagnetism, can't be, because there are effectively currents that are set up in the universe that cancel out the action of that force in a certain sense. It's a little bit inaccurate, but that will do. Okay, so the idea is that these guys become massive, but these guys remain massless. This is another force of nature, the strong interaction. Let me not digress too much about this. This is what is keeping quarks bound into protons and neutrons. That force is also driven by the exchange of a bunch of massless particles called gluons. So these things stay massless, but this thing becomes massive. That's the idea, and therefore this weak interaction is very short-range. Actually, the strong interaction is also short-range, but for a different reason, and that's a different public lecture. And let me not go there. Okay. All right. So I've made you concentrate on some very subtle ideas in physics for the last 20 minutes. Let's look at a picture of some humans. So these are the people that have been involved in these developments. It's a longer story than this. I haven't shown you the pictures of the guys who understood superconductivity, Bardeen, Cooper, and Schrieffer, and got the Nobel Prize for that. These are developments that started occurring just a couple of years later, because what happened was that people working in particle physics, something completely different from the behavior of currents in metals, some of these guys understood that the kind of physics that was introduced to understand superconductivity actually had potential implications for the universe at large, for elementary particles. And Nambu, who won the Nobel Prize a couple of years ago, working with Giorgio Lasinio, an Italian physicist, they pioneered the transference of an idea from what is called condensed matter physics, the physics of ordinary objects, into elementary particle physics. And Nambu was honoured with a Nobel Prize just a couple of years ago. Another condensed matter physicist who helped do this was called Philip Anderson. He won a Nobel Prize for something different a little while earlier. The mechanism that the LHC is designed to discover, the Higgs mechanism, is named after this gentleman. He's a Scottish guy called Peter Higgs. And here you see him with a hard hat touring CERN. I don't know exactly which detector he's looking at here. Is it the Atlas detector, Elisabetta? Okay, it is the Atlas detector. Of course it would be, because we're involved in that collaboration. Anyway, the particle that the LHC is trying to discover, which would tell us that the universe is a superconductor, is called the Higgs boson, typically, or the Higgs particle, and it is named after this guy. And maybe one day very soon, he will get a Nobel Prize. That is actually an interesting question. Let's forget about the physics and just talk about the sociology of who gets Nobel Prizes and so on. One of the problems with this, which is an endlessly fascinating topic for scientists, by the way, one of the problems is that although it's called the Higgs mechanism, there are several other guys that also claim to have a very strong hand in the development of these ideas, as well as the condensed matter guy, Anderson. There are also these other physicists, Tom Kibble, Guralnik, Hagen, Brodt, and Engler. Most of them are alive. Only this guy has passed away, and fairly recently. These other guys are alive. And if you know your Nobel Prizes, you know you can only give it to 3 people in a given year. So there's greater than 3 people here who are laying claim to the invention of what is typically called the Higgs mechanism. So if in a month's time, the Atlas and the CMS experiments at CERN announce the discovery of the Higgs boson, it is not clear, I think, who will get the Nobel Prize, if anybody, because there are just too many people to choose from. Okay, so let's go back to the LHC. So here again is a shot of the tunnel. It's obviously a big thing. It costs a lot of money to build this object, and it involves international cooperation to build this object. It is a fantastic enterprise. It is a major project management task, quite apart from anything else, and very expensive. So, you need politicians, this is the House of Commons, you need politicians in the UK and zillions of other countries to decide that this is a good thing to do. It is a good thing for we have to convince politicians that it is a good thing to allow people like me and experimentalists, I'm a theorist, but experimentalists more particularly, to actually spend billions of dollars to build such a thing. And so what we need to do is to tell the politicians why it is we want to do this. You know, why is it so important to spend billions of dollars doing this rather than something else? Okay, so how do we do that? So I think I've struggled to explain to you what superconductivity is. I can only give you a general impression of how that works. Now, how am I going to explain to you or to a politician in the House of Commons exactly what the Higgs mechanism is, and to try to convince these people that the entire universe might be a superconductor and it's important for you to spend several $billion to prove that, right? So how do we do that? Okay, so explaining the Higgs mechanism is notoriously difficult, and I'm going to piggyback on pioneers in the field of trying to explain this thing to people who, haven't been technically trained in physics. So one of these people, back a few years ago, was the Minister of Science in the United Kingdom, and he got a little bit sick of not understanding what the Higgs mechanism was. So he said, right guys, I'm going to set up a competition, and you guys are going to go out and you're going to compete for the best possible explanation of what the Higgs mechanism is to me. And me being a typical layperson, the UK Minister of Science. Okay. So the prize was something like a bunch of alcohol. And the winner was this guy, who I think I met once, from University College London. So let me show you what the winning entry looked like. And I think this is the best layperson's explanation or images. It forms the best images of what the Higgs mechanism is to people who are not technically trained in quantum field theory. Okay, so here's a typical thing for physicists to do. Physicists are party animals. They like going to cocktail parties. So here you have a typical group of physicists. They're all dressed in blue. That will not surprise you. It will not surprise you that most of them are male, unfortunately. So here is a group of physicists, a sea of physicists at a cocktail party. And the idea is this, that the universe is full of a field. This field is called the Higgs field. This is permeating the entire universe, and this Higgs field is like the Cooper pairs that are permeating a superconductor. Okay, so that's the analogy. But I have to jiggle two analogies here. One is Cooper pairs to this Higgs field, and the other is Higgs field to this sea of physicists nicely chatting and having cocktails at some party or other. Okay? So we have a room filled with these ladies and gentlemen. Okay, and then there's a door to the room. And from the door emerges a more brightly coloured guy, and he's kind of famous. He bears a certain resemblance to Albert Einstein. He's a famous physicist. And physicists love celebrity like everybody else. Okay, so suddenly the room becomes aware that a famous physicist, much more famous than these people, has entered the room. So what is their natural reaction? The natural reaction is to mock the guy, obviously. So suddenly all these people want to talk and touch this famous physicist. And all Albert wants to do is walk across the room. But he's prevented from doing it because he's mocked by all these physicists. So this is meant to be analogous to particles becoming massive. So the idea of the Higgs mechanism is that this is responsible for the creation of all of mass in the universe, as I said at the start of the lecture. And so Albert Einstein here begins life as the analogue of a massless particle, a particle that always wants to travel at the speed of light. And when a particle picks up a mass, it no longer travels at the speed of light, it slows down. So Albert, walking across this room and being impeded in how fast he can walk across the room because of these physicists that are all crowding around him and interacting with him and slowing him down, this is analogous to what is supposed to happen. So the universe is supposed to be full of this Higgs field. This is a kind of molasses. And when other particles move through this Higgs field, they interact with it in the same way that the sea of cocktail drinking physicists are interacting with Albert. And they slow the particles down. Even if the particles are massless and want to move with the speed of light, when they interact with the Higgs field, they're slowed down. It's a force of nature, but it's different from other forces of nature because the source of the force is everywhere. This Higgs field is meant to be everywhere. Just like the Cooper pairs in a superconductor are kind of everywhere inside the superconductor. Okay. Now, that explains why particles moving through the universe and hence through this Higgs field become massive. But what is this Higgs particle that I'm talking about, which is what the LHC at CERN has been designed primarily to discover? And why does that have anything to do with how particles pick up mass? Well, here is another analogy dreamt up by David Miller. So now Albert has long gone, or maybe this is another cocktail party, and what happens is that rather than a famous physicist appearing in the room, somebody shouts, "Hey, a famous physicist is about to come, Albert is about to come." Okay? So it's a rumor, and it starts to spread through the cocktail party, okay? And the physicists, excitable people, start to crowd around and start talking about the fact, hey, Albert Einstein is about to come in. So they start crowding around and talking to each other. And so they start to form clumps because of the energy that is being fed into the room by this rumor being proclaimed. And so this clump of particles is meant to be, clump of people, sorry, is meant to be analogous to a Higgs particle. So it's an excitation in this Higgs field. So the idea is that the Higgs field is basically this tranquil thing that is this force field throughout the entire universe. But it can be excited. There can be ripples and waves on this Higgs field. And when you look at that quantum mechanically, these ripples and waves, this additional energy in the Higgs field, manifests as particles, just like electromagnetic waves manifest as particles, as photons. So the Higgs boson, the Higgs particle, is to the Higgs field exactly what the photon is to the electromagnetic field. And the analogy here is this spontaneous clumping of these physicists at this infamous cocktail party. Okay, believe me, is the state of the art. This is the best you can do to explain what the Higgs mechanism is. Okay, I said there would be one slide about symmetry breaking. I don't want to disappoint David, who gave me the title. So I don't want to talk about this too much because it's really too complicated for a Friday night. But here is the deal. Let's talk about magnets again, but not superconducting magnets, just ordinary magnets. So here is some kind of rock called magnetite. And the idea is, and the rock is composed of little, what are called magnetic domains. So these are little permanent magnet-like objects inside the magnetite. And when this magnetite is sufficiently hot, in the case of this particular material, above 580 degrees Celsius, this is called the Curie temperature, these magnetic domains are pointed in all sorts of different directions. So magnetic fields have a direction. You've all played with bar magnets and iron filings and so on. You know that magnetic fields have a direction. And if you take a magnetic material and you heat it, if you heat it sufficiently, what you'll do is you'll disalign all of the magnetic domains inside the material that are conspiring to give you an overall magnetic field, an overall direction for the magnetic field. So all the magnetic fields cancel out. But then as you cool the material, what happens is that energetically it's favoured that all of these domains start to line up. And so what happens is that as you cool this stuff below this critical temperature, suddenly what was not a magnet suddenly becomes a magnet. It develops a north and a south pole. But the important thing is that the direction of the north and south pole is arbitrary. It is driven by accidents, by fluctuations, by random events that happen to have occurred at the time when this metal was being driven through this transition temperature. And so it could be that one time when you cool the metal, the magnetic field is in that direction, and another time it's in that direction. You've tried to keep things exactly the same when you did these two experiments, but you got two different outcomes because they were driven by random fluctuations at the time this transition was happening. So this is the spontaneous part of symmetry breaking. So the idea here is in this high temperature state, there's no preferred direction inside this magnetite. All directions are equivalent. But when you cool it, one direction becomes favoured because that is the direction of the magnetic field. And that direction is chosen spontaneously, it's chosen randomly. And next time you do the experiment, it will be chosen in a different direction. So this is related to what is supposed to happen in the universe. There is an analogue of this that was supposed to have happened very, very shortly after the Big Bang, when the universe was extremely hot. So the idea is that above a certain very, very high temperature, the universe was in a disordered state like this, and then as the universe expanded and cooled, suddenly it went from this kind of state to that kind of state. And it experienced a kind of transition like the formation of a magnetic field, but it was not the formation of a magnetic field, it was the formation of the Higgs field. Okay? And if you want to know what the temperature is, the temperature is 10 to the 15 degrees. Okay, so here we're talking about 580 degrees for the formation of magnetism in this particular material, which you can find on planet Earth. But for the universe as a whole, to do the analogue of this, and hence to explore the origin of the Higgs field cosmologically, to explain why it appears in the entire universe, you have to heat the universe quite substantially to 10 to the 15 degrees. All right. So this was possible shortly after the Big Bang, but is certainly not possible now. So we are stuck with this Higgs field, and it's just as well, because if all of the particles, like electrons and so on, that have mass, suddenly cease to have mass, and that's goodbye mama. Okay, so how do we find the Higgs boson? Let me show you the CERN laboratory again, near Geneva. So here's a schematic of the ring. And so here's this 27-kilometer ring. And I mentioned that there are 4 points at which the two counter-circulating proton beams are made to collide. These are the 4 points. That one, that one, that one, and this one. These are access points, just to bring people and equipment down into the ring. So these two ones, in red, CMS and Atlas, These are the two, so around each of these points is a gigantic detector, particle detector, like I was showing you earlier. These are the two that are designed to discover the Higgs boson, which is a telltale signature that the universe is a gigantic superconductor. These other two experiments do different things, which I don't have time to tell you about. And the Australian groups are involved in this particular experiment called ATLAS. Here is another diagram of the situation. So I mentioned that the ring is about 100 meters underground, going under farmland and villages and so on. And so in certain areas, you have these excavated labs that are instrumented, and you go down in an elevator and you get to the lab. You have a control room, and you also have the detector. Here is the border between France and Switzerland. Here is Switzerland, here is France, and the ring actually crosses the border. Here is a schematic of the ATLAS detector. It's a gigantic thing. Again, here is a cartoon of a human. So this is the size of a substantial building. It needs to be that big because you need to, in order to identify the particles, you just need a lot of material. You need the particle tracks to separate from each other and so on. So this thing needs to be very, very large. And also these particles are moving so rapidly that in order for them to lose energy and to identify themselves through the process of losing energy, you need to get them to interact with a lot of stuff. So this thing is designed in a certain particular way in order to identify different kinds of elementary particles that come from the collisions of protons, which happen here in this inner region. So somewhere in here, protons will collide and will produce all sorts of elementary particles, electrons, other protons, pions, muons, also neutrinos, maybe completely new particles, that's what we're hoping. And they all stream out, they interact with the detector, and from the way they do that, we can identify what they are. So here is an example. Here is what the Higgs particle might look like. So two protons collide, and let's say they produce, one thing they could do is produce a Higgs particle plus junk. Junk here means other particles which are kind of commonplace, they're protons and stuff like that. We're not very interested in them. What we're interested in is this new thing called the Higgs. One of the things that the Higgs can do is to decay to two other particles. So the Higgs is an unstable particle. And it can decay to two other particles called Z particles. These are also related to the W particles of weak interactions. And these Z particles, in turn, are unstable. And they can decay to many different things. And in particular, some of the time, they will decay to electron, anti-electron or positron pairs, and muon, anti-muon pairs. The muon is like a heavy electron. And this is the kind of event that is depicted in this picture here. So the two protons have collided at this point, right in the center of the detector. All this blue stuff is the junk. The Higgs particle was also created in there, but it lives for a very short time. You don't see a track. What you see are the debris from when the Higgs decays. And so what you see here are two electrons. These are the two electrons, and these are the two muons. It just so happens that muons travel a much greater distance through material than electrons, and it's one of the ways that you tell different particles from each other, which is how far they travel in this kind of apparatus. So you know these two things are clearly muons, and these are electrons because of where they interacted with the detector. So this is one possible way that Higgs bosons could show up. Higgs bosons, as I said, are unstable, and they can break up in many, many, many different ways. And how they like to break up depends on how heavy Higgs particles are, and we actually don't know what their mass is. We need to measure that as well, because the theory actually doesn't predict what the mass is. It just gives a certain range for what it can be, but not a precise number. So one of the challenges of the LHC experiments is to design something with the flexibility that it will be able to prove the existence of Higgs bosons no matter what masses they have. And that will be achieved. So this is just one possibility. Okay, time for a movie. So courtesy of CERN, there's a graphic here, a little video of how this experiment works. So these things are proton bunches which are being accelerated in various different rings. There's a good reason for accelerating it through a bunch of rings and feeding protons from one stage of acceleration into another. Finally, they go into the big LHC ring, they counter-rotate, and then at a certain point, so here we are traversing the ring, there's some graffiti by physicists, so the protons are going around the ring, so we're following one bunch of protons, and coming the other way and about to have a head-on collision is another bunch of protons. These are the 3 quarks with 3 different colours. Let me not explain that inside a proton. So a proton is a little garbage bag of elementary particles. Here's a bunch of protons about to collide with another bunch in the Atlas detector right in the middle. So you design things so they collide right in the middle, and you can hear the bang. And all these other elementary particles come out. In this case, what you get is something called 2 jets. So this is not actually a Higgs boson that I've produced for you here. It's something else. We haven't discovered the Higgs boson tonight. This was something else. But this is how these detectors work. And you just do this over and over and over again. And actually the data rate at this experiment is just enormous. And so another one of the many challenges of this experiment is actually how to deal with the data, to have electronics fast enough and then to have data acquisition systems and a sensible way for managing the data and then distributing it around the world, including to Melbourne, in a sensible way. So it's a really huge, huge enterprise. And hopefully it will discover the superconducting universe. So in conclusion, this experiment is running. It's running extremely well. Some of you may know that soon after it first switched on, there was a problem. Some of the superconducting magnets blew up, essentially, because of inadequate electrical connections made in some of the conductors around the superconductor. So it actually blew up for a while and had to be shut down and repaired. That's been done, and ever since then, everything has gone extremely, extremely well. The physicists involved in the collaborations, and there are many thousands of these. I didn't mention this, but the 2 collaborations, Atlas and CMS, are each collaborations of about 3,000 physicists. Okay, so it's a sociological task to understand how you can get 3,000 physicists and engineers working together. So it's, it challenges it on every front. But anyway, amazingly enough, this most complex apparatus that has ever been built by humanity to answer some of the deepest questions in physics ever asked by humanity is working extremely well. And the Higgs boson. So, the Higgs boson is our best and simplest guess for how particles pick up mass and how the universe becomes superconducting. But there are other options, more subtle options, more complicated options, and we can't rule those out. So maybe the LHC will discover the Higgs boson as predicted by the theory, the minimal theory, or maybe it will discover a more complicated version of it. But whatever happens, it must discover something to do that job. We know particles have mass. The theory that all this stuff is embedded in works just too well for this not to be true. So it's either the Higgs boson or something that does the job. Whatever it is, the LHC will discover it, and the discovery of this is going to happen soon. It could literally happen in weeks, maybe months, maybe years. It depends on the mass of the Higgs boson. Okay, so stay tuned. So once this physics is discovered, we will have simultaneously discovered the superconducting universe and the origin of mass. So the story has been about that, but the LHC could discover a lot more, and I haven't had time to talk about that. It could discover what the dark matter is. We know that the universe has mainly dark matter in it, not ordinary matter, not ordinary atoms, but actually something whose identity we don't know yet, but we can see it gravitationally. So we don't know what the dark matter is, and it's possible that the LHC, through these high-energy collisions, will produce it. It might discover more exotic things like extra dimensions of space, tiny black holes, which scared the life out of certain people, but you notice that they're still around. And other fantastic things like supersymmetry, new particles, new forces in general. We hope that the LHC will not just discover the origin of mass, although that would be a stupendous thing in itself. We hope that actually it will open a whole new world of exploration and actually answer many more questions. And to be parochial for a while, Australia is playing an increasing role in this project through the formation of this ARC Centre of Excellence, and we're very grateful to the Australian Research Council for the funding that allows us to do this. we're really ramping up our activities, and we're becoming about twice the size that we've been used to being. So it's led from the University of Melbourne, and it involves, importantly, collaboration with Adelaide, Sydney and Monash universities. For those of you who want to read more about the superconducting universe, I highly recommend this article by Lance Dixon. He's a particle theorist in California. It's called From Superconductors to Supercolliders. It's in a magazine published by the Stanford called Beamline. Just Google Lance Dixon and superconductors and you'll find this as more or less the first hit. This is a very nice article which explains better than I could the physics that I've been trying to this evening. Thank you very much.
Very beautiful explanation of these very, very deep ideas and the excitement. I really felt the excitement there of the imminent breakthrough. I'm sure Ray will be happy to answer a few questions if there are any. Gentlemen, right on the end here.
Sort of semi-related to this lecture, but it's about coupling of particles to space itself. Why do photons get coupled to space and get stretched during the Big Bang, but other particles don't?
No, I mean, all particles would. All particles, and photons are not the only ones that get stretched. In fact, the universe is full of neutrinos, and they also get stretched. So photons are just the most famous of the particles that get stretched. So the idea here is, so now you have to think of electromagnetism as a wave. So as the universe, and a wave has a wavelength, the distance between successive crests of a wave. As the universe expands, this wavelength gets bigger. The expansion makes that wavelength get bigger. And so photons get larger wavelengths and they lose energy and they become colder and so on. It also happens to neutrinos, not just photons. Other things like, so the material that galaxies and so on are composed of are immune from that. But that's because of gravity. They actually clump together and they don't actually, so a galaxy is not expanding as the universe is expanding, it's staying together as a lump that doesn't change volume. And so that's just because of local gravitational overdensity and gravitational attraction in that local area.
Perhaps the young lady with the red scarf.
I have to admit, I cannot answer that. Sure.
When they actually enter the superconducting, is it their behaviour, is that related to temperature, or is that related to the actual properties of the superconductor? The fact that they actually pair up and...
Well, it's related to temperature because so what's important is that in a metal you have this lattice of positively charged ions. So you've got atoms, right? So atoms are neutral. But in a metal what happens is that some of the electrons get liberated from the atoms and they exist in a kind of a sea. So you've got this lattice of positively charged ions and then the sea of negatively charged electrons. And so the electrons are repelling each other, so they don't want to form pairs. On the other hand, there are positively charged ions there which are attracting the electrons. So you can imagine a positively charged ion here attracting an electron there and an electron there. So you can think of it as the two electrons being attracted to each other. They're not really in a fundamental sense, but only through the intermediary of the positively charged ion lattice. Now, that will not happen in any coherent way unless the ions stop jiggling around. They need to be sufficiently stationary for that to happen. Yeah, so it's a balance between the repulsion of the normal electrostatic repulsion of two electrons and this small tendency to clump together. And at low temperatures, for certain materials, and certain materials only, the attraction can win.
Gentleman at the back.
I liked the cocktail party story that was given to politicians to help them understand. But that's only half the story as far as politicians are concerned. The other part is, what are we going to get out of it? And I'd be interested if there was something that was presented to them. And I'll finish with one observation. Shakespeare knew about all this. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy.
Well, I agree with Shakespeare, and certainly the LHC will not discover the ultimate secret of the universe or anything like that. What it will do is shed more light on more things, but there will be a lot of things that remain mysterious. For example, I mentioned dark matter. It may be that the LHC uncovers what that is, but it may not. It depends on precisely what this stuff is. So in terms of benefits and politicians and taxpayers and stuff like that, this is a pure science activity. So we are being driven by just fundamental curiosity about the way the world works. That's what it is. And I am completely open and unashamed and proud of that. Okay? And what we do is convince politicians that in the pursuit of these pure intellectual goals, that much benefit is gained. It is not that the Higgs boson is suddenly going to make mobile phones even funkier. That is not going to happen. But when you push the boundaries of human knowledge, you inevitably have to invent cleverer ways of doing things. So famously, the World Wide Web arose out of the need of CERN, this laboratory, to communicate across a very dispersed campus, to communicate complex material and lots of data. The internet already existed, but it was hard to know what was on the internet. If you knew it was there, you could get it. Then how did you know what was there? And so CERN commissioned Tim Berners-Lee to develop a way that anybody who logged in at CERN could see what was on some computer somewhere there. And this was not done because the people at CERN thought it would be a good idea if Australians streamed MasterChef, into their lounge rooms the day after the episode. It was not on their minds at all. And yet this is a byproduct. And now we can't live without the World Wide Web. So when you push the boundaries of human knowledge and push technology and push the intellectual limits, first of all, the really smart people are interested in doing this, and it's good to amuse smart people. It's good for them not to be bored, I think, fundamentally. And you never know where it may lead.
Well, I think on that note, we might bring the proceedings to a close. Before I ask you to thank Ray again for a very, very nice lecture, we'd like to remind you that we have one final lecture in the July lecture program for 2011. Same time, same place next week, when Andrew Malatos will take us now from space into the cause of neutron stars and some of the most vigorous events in the universe. But if you're still thirsty for more, there are two further lectures I'd like to draw your attention to. The first of these on August 10 will be given by the famous Lawrence Krauss, an extremely entertaining physicist. And this will be in the Copeland Theatre, and not here, it will be on the other side of the campus. And I'd ask you to Google up, use that high energy physics tool, the World Wide Web, to find out exactly the time for that. It'll be about his recent biography of Richard Feynman, The Quantum Man. And then finally on August the 17th, Professor Lynn Francisconi from the City University of New York, a colleague from chemistry, will be celebrating the 100th anniversary of Marie Curie's Nobel Prize, which was actually that we're also celebrating this year. So thank you again for coming, safe trip home, and thank you again, Ray, for an excellent show.